Deep beneath the surface of the ocean exists a world where pressure becomes almost unimaginable. At just a few hundred meters below the waves, the water surrounding a submarine pushes with a force powerful enough to deform steel, crush empty metal containers, and destroy structures that were never designed for such extreme conditions. Yet inside that same hostile environment, human beings are sitting calmly inside a metal cylinder. They are breathing normal air. They are operating complex machines. They are communicating, navigating, and living inside a vehicle surrounded by a force that is constantly trying to compress it from every direction. The question is simple, but the engineering behind the answer is extraordinary. How can a hollow structure survive a pressure that can crush solid metal? The secret is not simply stronger steel. It is geometry. A submarine survives the deep ocean because engineers discovered how to transform an enormous crushing force into something the structure can resist. The shape of the hull, the materials chosen, and the way every component works together determine whether the submarine survives or collapses. To understand this challenge, we first need to understand the enemy, water pressure. Many people imagine water as something soft and harmless, but at great depths, water becomes one of the most powerful forces on Earth. The deeper an object travels below the ocean surface, the more water exists above it, and the weight of that water creates increasing pressure. For every 10 meters of depth, ocean pressure increases by approximately 1 atmosphere. At 10 meters, the pressure is already twice what we experience on the surface. At 100 meters, the surrounding pressure is more than 10 times greater. At several hundred meters, a submarine experiences forces equivalent to thousands of tons pushing against its structure. But the most dangerous part is not only the size of this force. It is the fact that the pressure attacks from every direction at the same time. A structure sitting on land mainly fights gravity pulling downward. A submarine fighting the deep ocean faces something completely different. The entire surface of the hull is being squeezed inward continuously, searching for the smallest weakness where failure can begin. At first, the obvious solution seems simple. Make the walls thicker. Use more metal. Build a stronger shell. And while material strength is important, engineers discovered that thickness alone cannot solve the problem. A thick structure with the wrong shape can fail before a thinner structure with the correct design. The reason is that structures do not fail only because of the amount of force they experience. They fail because of how that force is distributed. Imagine a flat metal plate under external pressure. The force pushes against the surface, causing it to bend inward. This bending creates enormous internal stresses because one side of the material is compressed while the other side is stretched. This type of loading is called bending, and bending is one of the most dangerous conditions for structural materials. Now imagine the same pressure acting on a curved surface. Instead of forcing the material to bend, the curved shape redirects the force around the structure. The pressure becomes compression that travels through the curve, allowing the material to support the load much more efficiently. This is why a simple circular shape can survive forces that would destroy a flat one. The same principle exists in nature. An eggshell looks fragile, but its curved geometry allows it to distribute pressure across its entire surface. Ancient architects used the same idea when creating stone arches capable of supporting massive structures. The submarine hull uses this same engineering principle, but at a completely different scale. The circular cross-section is not a design choice made for appearance. It is a survival mechanism. A submarine built like a rectangular box would have weak points where flat surfaces could bend inward under pressure. But a cylindrical pressure hull spreads the force around its entire circumference, allowing the structure to resist the ocean's crushing force. However, engineers discovered something even more fascinating. The cylinder is not the perfect shape for pressure resistance. The perfect shape is a sphere. A sphere distributes external pressure equally in every direction, creating almost no weak points. This is why deep-sea exploration vehicles designed to reach the deepest parts of the ocean often place humans inside spherical pressure chambers. At the bottom of the Mariana Trench, nearly 11 kilometers beneath the surface, the pressure is more than 1,000 times greater than at sea level. Any ordinary structure would be destroyed instantly. But a carefully engineered sphere can survive where almost nothing else can. So if the sphere is the strongest shape, why are submarines not giant metal balls? Because engineering is always about compromise. A sphere is excellent for resisting pressure, but it is inefficient for movement, internal space, and carrying the equipment required for a long mission. A submarine must travel through water, carry engines, sensors, crew, and supplies. It needs the strength of a sphere but the practicality of a long vehicle. The solution was a brilliant compromise. A cylindrical pressure hull with rounded ends. A shape that combines the strength of curved geometry with the practicality needed for underwater travel. But the shape alone is not enough. Because even the strongest design must survive the hidden forces that appear inside the metal itself. And this leads to the next engineering challenge. How do engineers stop a submarine hull from suddenly collapsing inward when the pressure becomes too great? The biggest challenge for a submarine is not simply surviving pressure. It is surviving the way pressure causes structures to fail. A common assumption is that a submarine hull would slowly bend inward as it reaches deeper water, but the reality is far more dangerous. The failure can happen suddenly through a phenomenon engineers call buckling. Buckling occurs when a structure under compression loses its ability to maintain its shape. Instead of gradually deforming, a small weakness can trigger a rapid collapse that spreads across the entire structure. For a submarine operating hundreds of meters below the surface, this difference is critical. There is no slow warning. There is no time to repair the damage. Once the pressure hull begins to buckle, the surrounding ocean can force the entire structure inward almost instantly. To prevent this, submarine engineers do not rely only on thick metal walls. Inside the pressure hull, they install powerful circular reinforcement rings that act like the skeleton of the submarine. These internal rings support the cylindrical structure and prevent the hull from collapsing between reinforcement points. The idea is similar to the wooden rings around a barrel. Without those rings, the curved walls would lose their shape. With them, the structure becomes far more resistant to external forces. But designing these reinforcements is a complex engineering problem. The size, spacing, and thickness of every ring must be carefully calculated. Too little reinforcement and the hull becomes vulnerable. Too much reinforcement adds unnecessary weight, reducing the submarine's efficiency and performance. Every decision becomes a balance between strength, weight, and mobility. And this balance continues with the material itself. The pressure hull is built from materials specifically engineered for extreme underwater environments. Traditional steel is not enough. Submarine-grade steels must combine several properties at the same time: extremely high strength, resistance to cracking, and the ability to survive repeated pressure cycles. The metal must be strong enough to resist the ocean, but also predictable enough that engineers can accurately calculate its limits. Some of the most advanced submarines take this even further by using titanium alloys. Titanium offers an extraordinary combination of strength and low weight. It can withstand enormous stresses while reducing the overall mass of the submarine. This allows certain designs to operate deeper and perform in extreme environments. However, titanium creates its own engineering challenges. It is difficult to manufacture, difficult to weld, and extremely expensive to work with. During welding, even small contamination can weaken the material because titanium reacts easily with gases in the atmosphere at high temperatures. Building a titanium pressure hull is not simply a construction project. It is a demonstration of advanced metallurgy and manufacturing precision. But even the perfect material and perfect shape face another challenge. A submarine cannot be completely closed. It needs openings. Crew members need access hatches. Sensors need external connections. Weapon systems require launch tubes. Propulsion systems need complex pathways through the structure. Every opening creates a potential weakness. The reason is simple: a perfect curved surface distributes pressure smoothly, but an opening interrupts that pattern and creates areas where stress can concentrate. Engineers solved this by carefully redesigning the geometry around every penetration point. The edges are reinforced, the shapes are optimized, and the surrounding structure is strengthened to redirect forces away from vulnerable areas. Even the submarine hatch follows an important principle of pressure engineering. At extreme depths, the ocean pressure pushes the hatch toward its frame, helping maintain the seal. Instead of fighting the pressure, engineers use the pressure itself as part of the locking system. This is a perfect example of engineering philosophy. The best designs do not always fight nature. They use nature's own forces to create stability. But the visible shape of a submarine can be misleading. When we look at a modern submarine, we see a smooth outer body designed to move efficiently through water. However, that outer shell is not the structure keeping the crew alive. Many submarines use a two-hull design. The outer hull is called the light hull. Its purpose is hydrodynamics, reducing drag and allowing the submarine to move efficiently. Water can surround this space because the pressure is equal on both sides. The true survivor is hidden inside the pressure hull. This inner structure is the strong cylindrical chamber that maintains normal atmospheric pressure for the crew while the ocean outside tries to compress it. Between these two hulls are important systems, including ballast tanks that control whether the submarine rises, sinks, or remains at a specific depth. When the submarine needs to dive, seawater enters the ballast tanks, increasing its overall density and allowing it to descend. When it needs to rise, compressed air forces the water out, reducing density and restoring buoyancy. By controlling this balance, submarines can move vertically through the ocean with remarkable precision. But even the strongest pressure hull has a hidden enemy that cannot be defeated by shape or material alone. Time. Every dive creates stress. Every return to the surface releases that stress. And over thousands of cycles, the metal itself slowly changes. The next challenge of submarine engineering is not surviving one extreme dive. It is surviving a lifetime of them.